Hey everyone, welcome back to Calculus 3. This will be lecture 16 of the course. And in this section we're going to talk about the chain rule, and obviously in the context of functions of several variables. And so we're going to talk through what does it mean, what does the chain rule mean when I have a function of two or more independent variables. Okay, so let's go ahead and jump into it. And so this will be, we'll call this section 3.5, chain rule for functions of several variables. Okay, so in our previous session, we talked about differentials, which you will recall. So we just talked through differentials, and that's going to provide the basis for our extension of the chain rule to functions of more than one independent variable. Now in in this pursuit there's going to be basically two cases that we're going to need to consider. So there's going to be two cases. The first one, case one, which is obviously where we'll start, is going to involve w as a function of x and y. So the first case involves w as a function of x and y, right? Where these two guys, x and y, are themselves functions of a single variable t. Okay. Okay, so that's where we'll start. But just so that we know where we're going and we know what to keep in mind as we're going through this first case, let's talk about the second case. Second case is going to involve w as a function of x and y, where x and y are themselves functions of several variables, right? So they're not going to be functions of a single variable, they're going to be functions of several variables. So the second case will involve w as a function of x and y, where x and y are functions of several variables. So they could be two or more, right? Several variables, and we'll say it'll look like something like this: x equals g of st, and y equals h of st, right? So you'll have this x part and this y part, and they'll each have s and t, right? Multiple variables. Okay, so let's talk about the first case first. Okay, and so we're going to just toss out the theorem and then we'll do some examples and talk it through. Now here's what the theorem states. Okay, so let's let w equal f of xy. Okay, so w is a function of x and y, where of course f is a differentiable function of x and y. Right, and we mean differentiable in the sense from the previous lecture, right? The partial derivatives exist and they're continuous. Okay, so then if x equals g of t and y equals h of t, where g and and h are differentiable functions of t. I won't write that, but that's implicit, right? Well, let me write it. If x is equal to g of t and y is equal to h of t, where g and h are differentiable functions of t, then w is a differentiable function of t as well. Okay, and specifically, how would we identify that derivative? Well, here's what we would do. We would say dw dt is equal to the partial of w with respect to x times the derivative of x, the function x, with respect to t, plus the partial of w with respect to y times the derivative of the y function with respect to t. So it's kind of like the inside function, outside function times the inside function plus the outside function times the inside function. Okay, so very similar to the previous chain rule, but of course, here we're talking about partial derivatives, and as such, there'll be this this sum component here, right? So this sum operation. Let's do an example to see how this plays out. Okay, so let's let w equal x squared y minus y squared, where x equals sine of t and y equals e of t. Okay, and let's find the derivative of w with respect to t. And specifically when t is equal to 0. So let's find that derivative, the derivative of w with respect to t, and specifically evaluate it when t is equal to 0. Okay, and so we'll kind of go through this one in its entirety. So by the previous theorem, we know that dw dt is going to be equal to the partial of w with respect to x times dx dt plus the partial of w with respect to y times dy dt. Okay, and so you'll just have to reference the notes. They're a little off screen here, but basically this is really easy to do, right? We can just go and say the partial of w with respect to x, well, that's 2xy. The derivative of x with respect to t, that's cosine of t. And then the partial of w with respect to y is going to be x squared minus 2y. And the derivative of y with respect to t is just going to be e of t, e to the t power. Okay. And then, of course, all of these things, the x's and the y's, are all, so x we know is sine of t, y is e of t. So we want this to be a function of t because we're looking for the derivative of w with respect to t. So we can come in here and we can substitute the x and the y's all out for sine of t and e to the t respectively. So this would be 2 times the sine of t times e to the t, right? That's basically this part. And then, of course, cos t. And then plus, now this thing here is going to be sine squared t, that's the x, minus 2 e to the t. And then that's all times e to the t, right? So this part here is that guy. Okay. And then, of course, we could simplify this a little bit further, and we get 2 e to the t sine t cos t plus, and then this will be e to the t sine squared t minus 2 e to the 2t. I'm kind of distributing the e there. So then this is the derivative of w with respect to t. Okay, and can we evaluate this when t is equal to 0? Of course, right? So that's just going to be dw dt when t is equal to 0, and it's just basically plugging in a bunch of zeros here. So it'll be, what do we get here? 2 e to the 0 sine of 0 cos of 0 plus e to the 0 sine squared 0 minus 2 e to the 2 times 0. Okay, and so we know that's 2 times 1. Sine of 0 is 0. Cos of 0 is 1 plus 1. And then this will be another 0 minus 2e to, well, 2 times 1. Right. And so the whole shebang is just, this is 0, that's 0, and you get negative 2. Okay, so there we go, right? So we just use the chain rule to differentiate this function w. Function of x and y, which are themselves functions of are a function of a single variable t. Now, an alternative approach here, right, would be rather than use the chain rule, we could just plug in what x and y are equal to and differentiate with respect to t directly, right? So let's talk that through. An alternative approach would be to basically to write w as a function of t, right? And then just differentiate as normal. So let's talk that through. Let's do that example. So w, remember, was x squared y minus y squared, right? X is sine of t and y is e to the t power. And so this would be sine squared t, right, times e to the t minus 2e to the 2t. Right, so just plugging in e to the t for y there. Now we could differentiate this function as well. Right, that's just d dt of sine squared t e to the t minus 2e to the 2t. Right, so we could differentiate. This is going to require the product rule here. And so what do we get? We get, so differentiating the sign part first, so you'd get 2e to the t sine t cos t plus e to the t sine squared t. Okay. Yep. Yeah, that's right. Yep. And then that's this part here, and then this guy here would just be minus. Oh, that should be. Oh, that's not supposed to be a 2 there. Where that came from. This would differentiate down to be minus 2e to the 2t. Right. Now, does that match what we got up above? It does, right? So this is the same 2e to the t sine t cos t plus e to the t sine squared t minus 2e to the 2t. Of course, that's the same thing as what we have here, right? So this chain rule with multiple variables, the first case anyways, is something that could be done just by substituting the, just by rewriting the function w as a function of t rather than as a function of x and y. Okay. So that's useful to see, useful to note. All right. Okay, so we obviously the theorem just describes the chain rule when you have a function of x and y, but this can be extended, this case can be extended to pretty much, you know, functions of any number of variables, right? So the chain rule can be extended to functions of any number of variables. Right, the formulation should be straightforward. It's dw of dt, that's what you want to find. You've got a function w. And to identify the derivative of w with respect to t, now we'll assume that w has n variables. Okay, then this derivative is simply the partial of w with respect to the first variable times dx1 over dt plus the partial of w with respect to the second variable times that's an x, sorry, dx2 over dt plus, and then dot 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 plus the partial of w with the with respect to the nth variable. Okay, right. So the case we looked at just had 2, but we can easily extend that to as many as you like using this sort of formulation. Okay, all right. So that's the chain rule for the case where w is a function of x and y are functions each of t. Okay, so that's kind of the simpler case. Now let's do an example of this that's a little more challenging than simply calculating the derivative and following the formula. So let's do an example. So let's say we have two objects traveling in elliptical paths. Okay, so we've got two objects traveling in elliptical paths, and let me just kind of draw a picture of what these things are doing first, and then we'll flesh out precisely what equations they obey. right? So I've got my x-axis and I've got my y-axis. Okay, so let's say the first function kind of goes like this. Okay. Well, it's not a function, but it's say we have a set of parametric equations, and this is the path. I shouldn't write function. That's totally wrong. So path 1. Okay. So it's kind of spinning around like this over a very precise path. And then the second path is similar, but it's kind of turned and it's more vertical, right? So it's spinning like this. Okay. So I've got these two objects traveling in these elliptical paths. Now they obviously overlap. And so let's say, for example, one of the objects could be like right about here at a certain time, and another object is over here at a certain time. What we want to be able to do is we want to be able to identify the rate. We want to identify at what rate the distance between the two objects is changing for any value of t. Right, so you're going to have a certain distance here. Okay, so what we want to be able to do is identify at what rate is the distance between the two objects changing when, and we'll just say t is equal to pi. Right, so we want to find it for a specific t, but then really any for any t. Okay. Okay, so particles flying around here, intersecting each other on two separate paths. There's a distance between them at any time t. Like if I were to freeze the picture at any time, I could calculate the distance, right? And what I want to do is come up with some kind of a function or some kind of an equation that tells me what that distance is for any time t. Okay. Now let's say we have parametric equations describing these paths. Okay, so we have x1 equals 4 cosine of t, and y1 equals 2 sine of t, right? So these two together describe one of these particles, and then separately x2 would equal 2 sine of 2t, and y2 is equal to 3 cos t. Okay, so these two describe one particle, and then these two describe another one. So one of the paths is x1 and y1, and the other path is x2, y2. Okay, right? So that's the setup. Okay, so that's the setup. So what we're interested in is the distance, right? We're interested in the distance between the two particles, and we could easily, like if we were to freeze the image as we have here, we could calculate what this distance is, right? We know how to do that. S is equal to, we'll call the distance s. That's going to be simply x2 minus x1 squared plus y2 minus y1 squared. Right? So that's the distance. Now what are we interested in? Well, what we want to know is we want to know what the derivative of s is for some t, for any t, right? So we are interested in ds dt, and specifically when t is equal to pi, right? So when you plug the value of pi in, what do you get? Okay, and so s, as you can see here, is a function of how many variables? 4. Right, so this is an example of where we'll have to use the, and each of those, well, s is a function of 4 variables. x1, x2, y1, and y2 are all functions of t. So they're functions of a single variable. So this is a perfect example of where, of our case 1 chain rule, where we'll have more than just 2 variables. Okay, so what we need to specifically calculate what we specifically need to identify is ds dt, right? And let's write this out. So it'll be the partial of s with respect to x1 times dx1 over dt plus the partial of s with respect to x2 dx2 dt plus, we'll need the same thing for the y's, right? So we need the partial of s with respect to y1, and then finally y2. Partial of s with respect to y2 times dy2 dt. Right, so this one is somewhat more complex than the previous. You're going to have 1, 2, 3, 4 partial derivatives to calculate, and 4 regular derivatives with respect to t to calculate. Okay, and so we can do this. We can do this. So let's talk through each piece here. Right, so I've kind of done some of these ahead of time just because it would take probably an hour or half hour to do it all on the fly, and I don't want to bore anybody. So let's start with the partial of s with respect to x1. Let's start with that piece. Okay, so what is that? Well, that's the partial derivative of the function x squared minus x2 minus x1 squared plus y2 minus y1 squared to the 1/2 power. So it's this derivative, right? Okay, now can we calculate that derivative? Yeah, I mean, this is kind of ugly, but as soon as you realize it's a partial derivative, it's pretty straightforward, right? So you have to use the chain rule on this. And so what you end up with is 1/2 times x2 minus x1 squared plus y2 minus y1 squared. And then, so that's the derivative of the outside, and that's negative 1/2. And then you have to take the derivative of the inside, which would be a mess, except this is a partial derivative. So really, we're just interested in, this is the only variable, everything else is a constant. So this is 0 when we differentiate, and all we're left with is this piece here. So what you end up with is 2 times x2 minus x1, x2 minus x1, and then the derivative of that, you have to actually use the chain rule a third time, is negative 1. Right, so you get this. Okay, and this cleans up nicely, so it's a mess right now, but what you end up with is, you can see that the 2 and the 1/2 will cancel, so you'll have this guy on top, so it'll be negative x2 minus x1, all divided by the square root of this. Okay, and so it looks like that. Okay, and so this is okay. And now, in theory, we'd have to do this for all 4 of them, wouldn't we? Right, we'd have to do this for all 4 of them, and you can do it, and you'll notice that there are some nice patterns that begin to emerge. I'm not going to do it for all 4 of them. I'll just leave that to you guys. But we can evaluate this at t equals pi, because we'll need to plug that into our expression. Oh, sorry. Nope. Before we do that, we have to calculate the other thing. Right, so we'll need to evaluate this at t equals pi, but first we need to know what x1, x2, and all of those things are. They're the functions of t, right? So we have to figure out what those are all worth. Okay, so what is x1? x1 is 4 cos t. What is x2? It's 2 sine of 2t. y1 and y2, what are those two equal to? Well, 2 sine of t, and y2 is 3 cos 2t. Okay, we can evaluate each of these at t, or at t equals pi. All right, so what do we get? Well, 4 times cos of pi is negative 4. 2 times sine of 2 pi is 0. Right, sine of 2 pi is 0. 2 times sine of 1 pi is also 0. right? Sine of pi is 0. And then 3 times cosine of 2 pi is, so cos of 2 pi would be 1, so that would be 1 times 3 is 3. Okay, now these values here can be used to evaluate this function, this derivative at a specific value of t, right? So let's do that. So del s, del x1 when t equals pi, what do we get? Well, that's going to be negative, and again, I'm just using what's right here, and I'm plugging in what is x2 when t is equal to pi? Well, it's 0, and so on. So let's write them all in there. So negative, then you get 0 minus negative 4, right? x1 is negative 4. And then down below, you would get the square root of, and then it's 0 minus negative 4 squared plus, and then it's 3 minus 0 squared. All right, so up top, you obviously get negative 4. Down below, you get 5. Okay. All right. And so that's the value of the first partial derivative that we need to find for our calculation. Now remember, we got quite a few of these to do, right? So remember, we have to do all of these. All we just calculated was this guy here. This is what we just did. All of these are very similar. They have very subtle differences, and I think if you just look at that last, to figure out what each of these are, you can just look at this one and just look at that last iteration of the chain rule where you went inside the inside function, and the numerator will be different on these. Otherwise, they're exactly the same. Okay, but how do we get this piece of the expression, the derivative of x1 with respect to t? Well, that's just going to be the derivative of this guy, isn't it? And then plug in t equals pi. Right, so dx1 over dt, right, and specifically when t is equal to pi, that's just going to be ddt of 4 cos t evaluated at pi, which is going to be negative 4 sine of t, which we'll just plug in the pi here, right, and so you get a 0. Okay. And so this gives us the first term in our expression. So del s del x1 times dx1 dt is equal to negative 4/5 times 0. Right, so obviously 0. Right, so kind of flipping over to our previous, so this would be negative 4/5 times 0. Now we just have to do it the same thing 3 more times. Right, but as I said, the partials here are really easy to find once you found the first one. It's all of a pattern. Okay, and so what do we get at the end of the day? Right, so what do we get at the end of the day? Well, so del s del t is equal to, you get negative 4/5 times 0 plus negative 3/5 times negative 2 plus 4/5 times 4 plus 3/5 times 0, right? And so what you end up with here at the end is 22/5. So that's the rate of change of the distance between the functions, or between the two particles, in our, right, these particles flying around, zooming around, and there's always going to be some distance s between them, and when t is equal to pi, the rate of change of that distance is 22/5. Okay. All right, perfect. So that kind of brings us to the end of the case 1 examples. So let's talk about what happens in the other examples. So the other type of composite function, as we said, is one in which the intermediate variables are also functions of more than one variable. Right? So the other case is the case in which the intermediate variables, the x's and the y's are themselves functions of several variables. Okay. So for example, right, if w is equal to f of xy, and x is a function of s and t, and y is a function of s and t as well, right? This kind of situation, right? Before you had x to be as a function of purely t, and y is a function of purely t, but now you have the more mixed case, right? So the way to kind of think about this is that w is essentially a function of s and t. Right, it's essentially a function of s and t. Right, and in this type of example, it might be useful. In some cases, it's useful to substitute the equations x and y, g and h directly into the equation w. So to rewrite w as a function of s and t. Right, so it is sometimes, I'll just write this down, it's sometimes useful to write w as a function of s and t. And that's extremely straightforward. Let's do an example of that. Let's talk through an example. Let's find the partial of w with respect to s and the partial of w with respect to t for the equation w equals, let's just make it 2xy, where, and then let's say that x is equal to s squared plus t squared, and y equals s over t. Okay, so this exactly fits this scenario, right? You've got w as a function of x and y, and x is a function of s and t, and y is also a function of s and t. Okay, and so you could easily rewrite w in terms of s and t, right? W is equal to 2xy. Well, that's just equal to 2 times s squared plus t squared times s over t. Right, so you can write it like that. Right, and so how would we, let's see, we could simplify this. We could maybe write it like 2 times s cubed over t plus st. Right, so kind of combine. So now w is a function of s and t. And so it's real easy to find the partial of w with respect to s by just taking the partial derivative of this, right? And the same thing with the partial with respect to t. So del w del s is equal to the partial derivative of s of this, 2 times s cubed over t plus st, right? And what is that? Well, that's going to be equal to 2 times, now we need to differentiate this all with respect to s, so pretend t is a constant. And you could just write this as 3s squared over t plus t, right? And so you would get 6s squared over t plus 2t, and maybe you combine the denominator, so 6s squared plus 2t squared over t, right? So that would be good. That's your partial with respect to s. Right, and remember, so this is the second case where w is a function of x and y, and x and g and x and y are both themselves functions of 2 variables each, right? So we can, always just combine. We can always just rewrite w as a function of s and t. That's one way to approach it, and then the partial derivative is straightforward. Okay. I won't bother with the partial of w with respect to t. It's exactly the same as the previous part, right? So you can easily just do that on your own. There is an alternative approach to this, and that's going to involve the chain rule, right? And in some cases, this alternative approach is more straightforward and easier to work with, all right? So what is the alternative? Well, let's let w equal f of xy, where f is a differentiable function of x and y, of course, x and y, then if x equals g of st and y equals h of st, okay, then what? Well, how can we find those partials? Well, it's going to be del w, the partial of w with respect to s is going to be equal to take del w del x times del x del s, and then the same thing for the y's. So partial of w with respect to y and the partial of y with respect to s. Okay, so in this scenario you have partial partial plus partial partial, right? And then the same thing is true for the t, right? But let's write it out so we can kind of help make the pattern more obvious. So del w del x, partial of x with respect to t, plus del w del y del t. So it looks like that. Right, so pretty straightforward, I think. So let's use this approach to the with the previous example. Okay, let's use this approach with the previous example. Right, so w equals, what was it, 2xy, and x equals s squared plus t squared, y equals s over t. Okay, we want to find partial of w with respect to s. Well, according to the theorem we just looked at, partial of w with respect to s is equal to partial of w with respect to x times the partial of x with respect to s plus partial of w with respect to y times the partial of y with respect to s. Okay, so let's go through and just do all these. Are relatively simple functions, so we can do these kind of things in our head. The partial of w with respect to x, right? That's this guy here. What is the partial derivative of this with respect to x? Well, that is just going to be 2y. And then the partial of x with respect to s, that's this. And what do we get there? Well, we get 2s. This is a constant, so it'll just be 2s. And the partial of w with respect to y is going to be 2x. And then the partial of y with respect to s is just 1 over t. Okay, and so we can go back through this, and everywhere we have a y, we can plug in s over t. Everywhere we have an x, we can plug in s squared plus t squared, and we'll be home free. So we could rewrite this first section here as 4 times s squared over t. And then this guy here is to be 2 times, let's see, yeah, so this would be just 2 s squared plus 2 t squared all over t. Okay, again, just s squared plus t squared getting plugged in there, and then the 2 gets distributed, and the 1 over t is in the denominator. And then so this is 6s squared plus 2t squared all over t. Right, and so that's going to be the same answer as what we saw previously. So this is what we get now. And then with the alternative method, we had this. This was the method where we took w and we rewrote it in terms of s and t. Right? And then this way we kind of left things as they were, and we just used this alternative version of the chain rule. Okay. Excellent. Excellent. And so with this, in this scenario, we can, again, this is just examples where x and y are variables that are functions of 2 variables. This one could naturally be extended to as many variables as you want, each with as many variables as you want, right? It kind of gets messy, but there's a clean and easy way to do that extension, right? So let's say if w is equal to some function of x1, x2, dot, 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 xn, right? And each xi is a function of t1, t2 through tm, then the chain rule would work the same as what we just saw, right? So you would have del w with respect to t1 would be equal to the partial of w with respect to x1 times the partial of x1 with respect to t1, right? Plus, and then the partial of w with respect to x2 times partial of x2 with respect to t2, right? Sorry, with respect to t1, right? And so this would go on and on here, and I'm just going to abbreviate this. So partial of w with respect to xn times the partial of xn with respect to t1, right? That's the first one, and then this would go on and on until you got the partial of w with respect to tm, and that would be equal to the partial of w with respect to x1 times the partial of x1 with respect to tm plus plus the partial of w with respect to xn times the partial of xn with respect to tm. Okay, and everything in between. Right, there's a whole bunch of partial derivatives, right? Especially when you have n variables, each of which is a function of m variables. So you have all these different options, different levels, and so you can kind of see how this would work. Okay. All right. Okay. Great. Let's do an example. Let's do an example where we use this. So let's say we want to find the partial of w with respect to s and the partial of w with respect to t when s equals 1 and t equals 2 pi for the function given by, okay, so here's w. W is equal to xy plus yz plus xz, where, so you've got x, y, and z here. So where x is equal to s cosine of t, y is equal to s times the sine of t, and z is equal to t. Okay, so kind of writing these all out. Right, so this one partial derivative, w with respect to s, how would we go about that? Well, we would just follow this kind of pattern here, right? So we would be the derivative of w with respect to s in this case. It's going to be equal to the derivative of w with respect to s times the partial derivative of s with respect to, well, hold on. We'll just go through it. Let me just write it out. The variables are different, so I'll probably just confuse people if I write it that way. So the partial of w with respect to s, it's going to be the partial of w with respect to x times the partial of x with respect to s, plus, and we have to go through all the variables, not just x. We have to go through x, y, and z. So partial of w with respect to y times the partial of y with respect to s, plus the partial of w with respect to z times the partial of z with respect to s. So this is our formula. Okay, this is the formula we would use. Okay, so what is the partial of w with respect to x? Partial of w with respect to x. So looking up here at w, x is a variable, everything else is a constant. So it'd be y plus 0 plus z, right? So you'd get y plus z. Now what's the partial of x with respect to s? Well, this is x. Partial of x with respect to s, s is the variable, cosine of t is just a constant, so it'd just be cos t. Okay, and now this one, partial of w with respect to y, right? So variable, 0, so x plus z, right? And then sine of t. And then what about the last one? Partial of w with respect to z, right? So constant, variable, variable. So it'd be y plus x, right? And the derivative of z with respect to s? Well, in this case, t is treated like a constant, and so the derivative of a constant is just 0. Okay, so altogether, our partial of w with respect to s is just y plus z cos t plus x plus z sine of t. Okay, so now let's go through and evaluate this thing. Okay, so let's go through and evaluate this. Let me just rewrite it here. Del w, del s, we found was y plus z times cos t plus x plus z sine of t. Okay, and we need to know what the value of this partial derivative is when s is 1 and t is 2 pi. So it's frequently a good idea just to go through and figure out what all of the variables are when we're evaluating at a particular value. Right, so in this case, x is equal to s cos t, which is, in the case of s being 1 and t equaling 2 pi, this would be 1 times cos 2 pi, which is 1. What about y? Well, y is equal to s sine of t, and so again, that's 1 times the sine of 2 pi, and that's going to be a 0. What about z? Z is equal to t, so it's just 2 pi. Okay, and then we just plug it all in. So partial of w with respect to s when s equals 1 and t equals 2 pi, that is going to be equal to, well, 0 plus 2 pi times cos 2 pi plus, and then 1 plus 2 pi times the sine of 2 pi. Okay, and so that all evaluates nicely. This will be 2 pi times the cos of 2 pi. Okay, so that's going to be 2 pi times 1 plus, and then this will be 1 plus 2 pi times, and then sine of 2 pi is 0. So this would just be 2 pi. Okay, so that's how that one works. And it's the same idea for the other partial derivative. I think, oh no, we want omega w del t. Okay, and so I'll just tell you the answer there. That one is del w del t when s equals 0 and t equals 2 pi. That should be equal to 2 plus 2 pi. Okay, so we'll just let you guys work on that one. It works almost exactly the same. Almost exactly. Okay. Now, in the last section, the last thing we want to talk about here is what happens, how can we use the chain rule in the cases where a function is maybe not explicitly defined, but more like defined implicitly. So what about when a function is defined implicitly? Right, so like implicit differentiation, right? Okay, so let's talk through this again here just to kind of refresh our the way we think about this. So suppose that x and y are related. Suppose they're related by the equation f of xy equals 0. Okay, and let's assume that y equals f of x is a differentiable function of x. Okay, where it is assumed that y equals f of x is a differentiable function of x. Okay. So let's say we want to find the derivative of y with respect to x. Okay, so let's switch pages here. So to find dy dx, we can use implicit differentiation, right, as previously defined, kind of the same thing as what we've seen in the past. Okay, we can use implicit differentiation as previously defined. Okay. So we can do that, right? But the chain rule, right, what we've just described, provides a convenient alternative, right? So the chain rule provides a convenient, and we'll see that it is actually a very convenient alternative. Okay, so let's consider that w equals f of xy. And another way to write this, right, since y is a function of x, is to say this is f of x comma f of x, right, little f of x. Right, and we can just apply the previous theorem to this, pretty straightforward, right? So dw dx, right? The way to kind of think about this would be, you could write it like this: f, the partial with respect to x of xy times dx over dx, plus the partial with respect to y of xy, of f of xy times dy dx. Right, so this is just straight application of the previous theorem. Right, so in our previous theorem, this was the partial of w with respect to x times dx over dx, and this is the partial of w with respect to y times dy over dy. Okay, so and when I say our previous theorem, I mean the first theorem that we saw. Okay. So kind of hang with me here because we had this assumption that f was 0, big F was 0. So because w equals f of xy, which was equal to 0, and that's going to be true for all x, right, in the domain of f. All right, so all f, in the domain of little f, right, in the domain of little f. Okay. So because that's true, we know that the derivative is equal to 0 as well. Okay. Right, we know therefore that dw dx is equal to 0. Right, and so what do we have here? This previous thing here can be rewritten as, well, first let's just set this up. So f partial of x times x of xy times dx dx plus partial of y times dy dx. That equals 0. Well, we can basically rewrite this, right? Now, assuming that the partial of y is non-zero, right? Assuming that's non-zero, and noting, right, of course, that this probably stood out from the onset at dx over dx, that equals 1, right? Noting these two things, this is an assumption, this is a fact. Given this, it's true then that dy over dx is equal to negative f sub x xy over f sub y xy. Right, so the partial of x divided by the partial of y, that's the derivative of y with respect to x, when you have a function defined implicitly, right? And this of course assumes that this is non-zero. Okay. Right, and so this is I know that seemed maybe like a confusing explanation potentially, but this is a very convenient way to implicitly differentiate. All right, so let's talk about, first of all, let's summarize this in a theorem, kind of the need to know piece here. Okay, Okay, so if the equation f of xy equals 0 defines y implicitly as a function of x, well, then the derivative of y with respect to x, right, is equal to the partial of x, partial with respect to x, divided by the partial with respect to y, right, assuming that the partial with respect to y is non-zero. How slick is that? That's very nice, right? So, no more, like, you can, of course, always differentiate these things implicitly, but this is a very, if the partials are easier to identify, then this is a quicker way to do it. Okay. So, let's take a look at an example. Let's do an example of this. So, say we want to find dy dx for, this equation, for y cubed plus y squared minus 5y minus x squared plus 4 equals 0. Sorry, you got this equation here where we could say, okay, y is implicitly defined as a function of x, right? Obviously, it's not explicitly defined, and it would be very hard to separate this out and to write y explicitly as a function of x. But nonetheless, we maybe want to know the derivative of y with respect to x. Okay. So, of course, we can do that using the previous theorem. So maybe we say f of xy is equal to this guy. Right, so you've got this guy here. Right, so then we just need the partials. Partial with respect to x, partial with respect to y. Right, so f sub x. Right, now don't get confused by this notation. This is just this, right? Right, we're used, maybe, if we're used to this notation. I tend to use this notation more, but this is how the theorem's stated. So let's go with that. Right, so we just need to find the partial of this. So I'm kind of going the long way by using all the notation, but that's fine. I want to make sure people understand what we're doing here. And so in this case, actually, constant. The only term in here that isn't constant is this one, and so the derivative with respect to x here is really just minus 2x, isn't it? Okay, what about the partial with respect to y? Again, that's just partial of f with respect to y, partial of y of the same thing. I probably don't need to write it again, but I'm just going to make sure. I hate it when people I hate it when people get lost in the notation, like they get confused because the notation abruptly shifts. So I like to make sure that at least once or twice I kind of blend the notation together so people can see how each of these things are related. So here we've got 3y squared plus 2y minus 5, and then these are both constant, right? So that's the partial with respect to y. Okay, and what the theorem says is then that the derivative dy dx is just going to be negative, and then it's this one over this one. So looks like that, right? And then, of course, you get the negative and the negative, and so that becomes positive. And you have that beauty right there. Okay. Now, I don't know for sure if that's easier to do than, in this case, than just going through and implicitly differentiating this like Calc 1 style. But I got to think it's not harder. And in a lot of cases, I can imagine this would be easier. Right. So, very good. So that is that is the chain rule. Okay. And so I think we'll leave it there. And next time when we get together, the next lecture is going to be over something called directional derivatives and gradients. We're going to kind of get into some optimization style problems. Well, kind of the machinery behind some optimization style problems. So, all right, sounds good. We will talk to you all later. Take care.